Thanks for coming. Today we have Katja Nowack, who's from Stanford University. She's a postdoc in Cam Muller's group at Stanford in physics or applied physics?
I think I'm officially in applied physics.
That's it. Yeah, if you don't know, the applied physics program and the physics program at Stanford are like intertwined, so it really doesn't matter.
Yeah, Cam is affiliated with both. Yeah.
She came from Delft University in the Netherlands, where she did her PhD with Levin van der Suyten, who happens to be from Stanford University, doing well. She worked on gallium arsenide quantum dots, electrical readout and probing of double quantum dots. And then she came to Stanford to Cam's group and works on Telluride now in the quantum Hall regime. That's what she'll talk about today. There's a tea at 4 o'clock for graduate students and postdocs over at the CSS building. One of the tea cookies.
Yeah, I'd like to start thanking Len and also Jake, which is here today, for actually inviting me to give the JQI seminar. And I'm very excited to learn about all the great stuff you're doing here. And I think I've only seen like a tiny fraction of this until now today, but I'm looking forward to learn even more about it during the rest of today and also sometime tomorrow. And so during the next 45 minutes or so, I hope to excite you about some work I've done in Katja Nowack's group at Stanford University, and that is that we have started to image how the current flows in a Mercury Telluride quantum well in the quantum spin Hall regime. And actually just a few minutes ago we sort of had a very short conversation about the little view graph I have here on my first slide, and I actually was claiming that just by looking at this picture and understanding this picture, you essentially see my talk. So what you actually see here is a sheet at which where there's a current flowing at the edge. So that's a blue arrow here, that's a flowing current. And that current generates a magnetic field, and the field lines are shown in red here. And we are actually measuring these magnetic field lines using the pickup loop, which is this little tool which sticks out here, which is part of the SQUID we are scanning. And okay, so I will talk about this in much more detail in the coming few, in the next 45 minutes. So first of all, First of all, I should point out that that there has been many people who contributed to this work. So I'd like to thank all the people I've been working together with. Particularly Eric Spanton, which is a graduate student in Cam's group, has done part of the measurements I'll be showing, and I've contributed. I've also had lots of discussions and help from all my other lab mates. The experiments are done in collaboration with a group of David Gordon, specifically the samples are made in his group actually. The material is provided by the lab of Laurens Molenkamp from Würzburg, and then we also have a lot of support from our in-house theorists, Su-Cheng Zhang and Xiaolin He. The quantum spin Hall state is a manifestation of a two-dimensional topological insulator. So that means that it has a conduction band and a valence band, and it has an energy gap which separates the two. However, a key feature of the quantum spin Hall state is that it supports edge modes which have energies within the gap and which are localized at the edges of your device. And these edge modes are special if you have the boundary of a sample, like let's say this is a slab of material, then the edge modes will be, as the name already implies, be localized at the edges of your, or at the boundaries of your device. And at each boundary you will have two counter-propagating modes. One, in this picture, right-moving mode, and one left-moving mode. And these modes are spin-polarized in the sense that the left movers in this picture, or that the spin direction is linked to the direction of the propagation. So the left mover has a spin pointing up, and the right mover has a spin pointing down. And the spin polarization makes that backscattering between these two counter-propagating modes is suppressed, and so that you should, in principle, get dissipation less transport through these edge modes. And experimental, so this is a quantum spin Hall state in a nutshell, and one experimental system where the quantum spin Hall state is was predicted to be realized, and fairly soon after the prediction has also been demonstrated, are Mercury-Telluride quantum wells. To tell you what is special about Mercury-Telluride quantum wells, I'll start by telling you something about cadmium telluride. Here we are looking at the band structure of cadmium telluride, and it's fairly similar to gallium arsenide in the sense that it has a conduction band up here, which comes from the S-type, which is S-type in symmetry. And then it has a valence band down here, which is P-type in symmetry. By the way, please interrupt me at any point of my talk if something is not very clear. Mercury telluride has very strong spin-orbit coupling, and the strong spin-orbit coupling actually drives a so-called band inversion in Mercury telluride. So here you see the band structure of bulk Mercury telluride, and you'll notice that the S-type band, which was previously up here, and as indicated in blue, lies now below the P-type bands, which are here drawn out in red. And that's what people call an inverted band structure. So inverted band structure again means that the P-type, that your higher lying bands are P-type and your lower lying bands are S-type in nature. And now we're going to build a quantum well out of this material. And what I show here is a sandwich of cadmium telluride, then Mercury telluride and cadmium telluride. And the lines, you follow, let's say, the bottom of the P-type bands, or the K with 0 value of the P-type band, and that gives you one potential well here. And then the blue, you follow the maximum of the S-type band, and that gives you a second potential well here. And if you make the quantum very, very skinny and ask yourself, like, where are the lowest lying modes in this quantum well, there's a confinement energy added to the energy of the lowest lying modes in these two potential wells. So the dashed lines here are the lowest lying modes in the two respective potential wells. And you see that when you make the quantum well wider and wider, that these two lowest lying modes actually cross over. So here for the skinny quantum well, you see that the blue mode, which is the sort of the mode which derives itself from the S-type band, still lies above the mode which derives itself from the P-type red band. But then once you make the quantum well thicker, and the critical thickness at which these two modes cross is about 6.3 nanometers, you get in a situation where the red mode, H1, lies above the blue mode, E1. And so for a quantum well, only once you're above this critical thickness of 6.3 nanometers, the band structure of the quantum well is actually also inverted. And why is this interesting? So what Bernweg, Hugh, and Zhang have actually shown is that across this, when you cross the critical thickness, that your band structure goes from being topologically trivial to topologically non-trivial on this side. And this is a very serious way of saying this, and actually just the fact that you have a transition from being topologically trivial to non-trivial already tells you that there should be edge states present in these materials. However, there's also, I can also make somewhat more hand-waving arguments why once the quantum well is above the critical thickness and has this inverted band structure, why you should find edge channels at the boundary of a device. And for that, let's look now as a function, say, at this mode as a function of space. So imagine now x. So this was actually the growth direction of the quantum well, let's say. So now imagine you have a slab of this quantum well and you take a cross section along that slab. And so now I'm drawing out just like the energy of this mode E1 and H1 as a function of space. At some point you'll hit your sample boundary or device boundary, and then the bands have to curve up just because the electrons somehow have to stay inside your material. So that's the same as saying that once an electron comes to the device boundary, it sees a huge potential barrier. So the bands curve up in the way I've shown here. And so what I've shown here is the case of the trivial quantum well, the one which has a non-inverted band structure. If we draw the same picture, though, for the inverted one, where within the quantum well the H1 and the E1 level have interchange position, the bands in this case also have to curve up, but the outer world or the vacuum, let's say, has a normal band structure. So, and to connect what's inside the quantum well to what's outside in the quantum well, the band, or let's say that's the same as to say that the red band will still curve down when it hits the device boundary, and the blue band will still curve up once you hit the device boundary. And then unavoidably, somewhere close to the device boundary, you get these crossings, where actually the gap closes, and that's exactly where you will actually get edge channels, or why you get edge channels at your device boundary. Another way to actually convince yourself that there are these edge channels are that you can run tight binding calculations, modeling, or explicitly actually imposing a boundary to your device, and then you can, in a tight binding calculation, sort of calculate the energies of all the modes present in your finite-sized system. And if you do that for a non-inverted quantum well, you just find a gapped level spectrum with a gap here, and then once the band structure is inverted, you actually do find energy solutions which are within the gap, as shown here, and which are localized at your device boundary. Okay, so the important message, somehow there are edge channels in this material. And soon after this was actually predicted, there has been a set of experiments from the group of Laurens-Molenkamp, which can actually grow these structures, the Telluride quantum wells. And the first one showed that you do indeed find quantized conductance when you measure a Hall bar made out of this material. So what's shown here is, let's say you have a Hall bar, you pass a current from lead terminal 1 to terminal 4, and then you measure the voltage between terminal 2 and 3. And the conductance you get for sufficiently small device, and I'll come back to that later, is roughly 2e squared over h. And that is what you would expect if your transport in this structure is dominated by one-dimensional edge channels. That's like the 2e squared over h comes about because that is what, let's say, Landau or Büttiger tells you should be the conduction for dissipation as one-dimensional edge channel. So that was, so these measurements are for a, for the inverted quantum well. They have also done measurements for a non-inverted quantum well, which is the black curve here. And a non-inverted quantum well just goes insulating when you tune the Fermi level into the gap. So I'm sorry, actually, I explained to you that what's shown here is sort of a conductance measurement as described above. So that's actually the resistance which is plotted here. And here on this axis is actually the gate voltage of the top gate on top of your Hall bar, which tunes the Fermi level inside your structure. And so if you tune the Fermi level inside the gap in the non-inverted device, you just get an insulator. If you tune the Fermi level into the gap of an inverted device, you get this conduction 2e squared over h. And that is for a sufficiently small device, though. They have also done measurements on slightly larger devices in the many micrometer size. And there they find actually still a finite conductance, but it's not quite close to the 2e squared over h anymore. And that's actually one of the puzzles or the big open questions in the field. What makes these larger devices to not be perfectly ballistic anymore? There's been another follow-up transport measurements where they do non-local measurements where you have these H-bar type of structure where you, for instance, can pass a current from terminal 1 to 4 and probe a voltage between 2 and 3. And that's what transport people call a non-local signal. And if you have edge channels in these devices, actually you can employ Landauer-Bütteker formalism to predict what this non-local signal would be. If you just would have a device conducting in the bulk, you would expect no or very, very tiny non-local signal. If your current is carried by these edge channels, then the current can really flow all via these edge channels all around your structure, and you can sort of come up with the magnitude of the non-local signal. And they found non-local signals which are very close to the expected values. And then finally, they've also done some experiments, which I won't go into more detail of, where they do see first signatures of the spin polarization actually of these edge channels. But so that's the set of experiments or the experimental investigations which have been done so far on the quantum spin Hall state in Mercury Telluride quantum wells. And there's very strong evidence for the presence of edge channels. There's also a lot of open questions, though. What happens, for instance, to devices which are larger than several micrometer? Why aren't the edge channels fully ballistic anymore? Why in the smaller devices the conductance values people find are not perfectly quantized? I mean, you might have noticed that the values are kind of close to 2e squared over h, but different from, for instance, the integer quantum Hall effect. It's not like spot on quantized. And so there's a lot of questions about like what limits the ballistic nature of these edge channels. So when we were looking at this, one of the so that I want many of these open questions we also cannot address with the experiments I will show to you, but like one thing which was very important to us was to first actually independently verify that these edge channels are present in the devices, and that's what I'm going to talk about next. So the idea of the experiment I'll be talking about is like actually very easy. So if you think about when you tune the Fermi level in your device from the valence band to the conduction band through the gap, you have certain expectations for the current flow. So when your Fermi level is truly in the valence band or the conduction band, actually your whole device or the sheet of your Hall bar is conducting, and so your current will just spread out through the whole bar. So here I'm actually already showing a little bit the structure we actually have measured. So we had a whole bar made out of Mercury Telluride quantum well. It has 6 contacts shown here. However, because we wanted to scan above this whole bar, we could only contact the 2 contacts which are up here. So when we pass a current, we will pass it from this contact into this contact. And then on top of the structure, we actually have a top gate. And by changing the voltage on this top gate, we can tune the Fermi level in the Hall bar. And so when we tune the Fermi level into the valence band or the conduction band, we expect a current flow which looks roughly like this, where the current really spreads out through the whole bar. But if we tune then the Fermi level inside the gap, we should see that the current flows along the edge of the device, everywhere where the top gate is present, to put the Fermi level truly into the gap here. And then you would get a current density or current flow which more looks like this. And so that was our first goal, to just simply see this difference. And how are we going to actually...
Sorry.
Yeah?
On that last slide, so what was happening at the 2 ends, where it's on the right, where it kind of spreads out?
Here?
Yeah.
Yeah, so that's the end of the top gate, essentially. So the top gate, it's a little bit in a funny shaded color. The top gate, let's see if I can steady my hand enough, sort of only extends about this far beyond where this contact is. So it ends right here. And so where the top gate ends, actually the Fermi level is just where it is at 0 top gate voltage. And in the case of our devices, if you don't gate it, or at 0 top gate voltage, the Fermi level is actually in the conduction band. So meaning that the slab of material which is ungated is a homogeneously conducting slab of piece of material. And so then that's why it spreads out here again. Now, how are we going to image the current? We do that by, so now comes the picture from my first slide again. So you have a current flowing as depicted here that generates, by a BSOR, you can compute what kind of field lines that generates. And then we go in with a pickup loop, which is attached to a SQUID. We measure the flux through the pickup loop, which is given by the convolution of the Z component of the magnetic field times what we call the point spread function of the SQUID. And the really nice thing of this technique, other than many of the other imaging techniques which people actually are trying to employ to look at this material, is that it works through a top gate, because the magnetic field lines just go straight through the gold metal electrode we use to gate. And this is a more technical advantage, because it is kind of problematic to grow these quantum wells to be truly undoped. And so you need to gate to get the Fermi level truly into the gap. But if you have to use a backgate, then that has proven until now to be quite challenging. And so being able to use a top gate is a nice technical advantage. Okay, now I'm going to tell you a little bit more about the actual SQUID. So SQUID, to start with, is a superconducting loop interrupted by 2 Josephson junctions. We actually voltage bias our SQUID and measure the resulting current as a function, which is, if you put flux through the SQUID loop, as a periodic function of the flux through the loop, as is in a cartoony way shown here. And our SQUIDs in the lab don't look quite as simple as this SQUID here. The SQUIDs we're using, so here you see the complete SQUID loop sort of folded back once onto itself. the two Josephson junctions are here. Most of the SQUID is actually covered by superconductor to shield it against any magnetic fields, so that the only openings where you can actually thread or feed flux into the SQUID are these openings here, which I will address in a second, and are these two little openings here, which we call the pickup loops. So let's say this is our pickup loop, and the sample will be close to this pickup loop here. And there's a second pickup loop out here because the whole design of the SQUID is gradiometric. So that you cancel general or potentially present global background fields. We have then a set of what we call modulation coils to feed additional flux into the SQUID into these two openings, and actually that makes that that enables that we can run the SQUID while measuring in a feedback loop. So we can keep whatever whatever kind of flux the pickup loop picks up here, we can sort of compensate by feeding signal into the modulation coils and stay at a fixed working point. And then finally, and that's a feature actually I'm not going to use in this experiment, but I will briefly come back to this in the outlook, we have so-called field coils which wind around both of the pickup loops, where we can run a current through. And if we do run a current through, we actually generate locally a magnetic field at the location of the sample, and then what the SQUID measures is actually the magnetic response of the device. And then again, because this design is gradiometric, actually what the pickup loop sees is really only the sample response, and is only the sample response because the field or the flux which is directly fed in from the field coil into the SQUID is equally fed into this pickup loop and this pickup loop, and those two, because of the folding, because of the gradiometric design, cancel each other out. And so that's actually a useful feature if you would want to look with the scanning SQUID at superconductors, as an example. Okay, so this is how the SQUID sensor looks in real life. So this is an optical image. So you see the pickup loop here. You see some of the magnetic shielding. You also see the field coil going around here. And then the whole thing sits on a large chip, which is quite significant in size. We polish this chip down to a sharp corner. And that sharp corner will be brought very close to the sample. And so we have a flux sensitivity with these SQUIDs of something like 2.5 microfarads per square root hertz. And at the typical scan height, we measure it. We measure at that will translate to a current sensitivity of roughly 15 nanoamps per square root hertz. At 10 hertz, at something like a kilohertz, the sensitivity is still improved by like roughly a factor of 3. It's a fairly complicated process to make these SQUIDs. It's an 11-layer fabrication process, and we don't do that in-house. Yeah, and then I've already addressed that it has a gradiometric design, that we run it with a linearized feedback, and that we have these on-chip feed coils. And then this is how a scanner then looks like. So we have a set of like 3 other cubes, which you see here for coarse positioning of this of the SQUIDs, and then on top of the other cubes we have mounted like a fine motion stage, which is based on piezoelectric S-benders, where here you actually get a top view onto this part here. So here's, for instance, this horizontal slab is our Z piezo bender. And the SQUID sits like on this little PCB board, just like right here at the corner of this PCB board. And that is brought under a very shallow angle, close to a sample substrate, as shown here. And the shallower we can make the angle, the closer actually the SQUID pickup loop will come to the device. And a typical alignment angle would be something like 4 degrees roughly. Okay, so that's how our scanning SQUID looks like. And so again, what we want to see with the scanning SQUID is that when we tune the Fermi level outside of the gap, that we get this homogeneously flowing current. And then if we tune the Fermi level inside the gap, we really want to see that the current flows along the edges of the device. And first of all, I show you here the actual two-terminal resistance of this whole bar as a function of top gate voltage. I can only measure two-terminal resistance because, again, I can only contact these two contacts of the whole bar because of the scanning. Nevertheless, the two-terminal resistance clearly shows a peak, and the peak value is much larger than 6/5 H/E squared. This number is there because that is what the Landau-Büttiger formalism would tell you you should measure in this two-terminal configuration if your edge channels are perfectly ballistic. And the fact that we see a peak value on the two-terminal resistance, which is much larger than this value, actually already tells you that the edge channels are not ballistic over the full length. And it's something very typical for these large devices. So I haven't pointed that out yet. Our whole bar is actually 50 micrometer long and 30 micrometer across. And so the truly quantized conductance you only find in whole bars which are several micrometer in size, but not beyond. But nevertheless, so the conductance peak actually tells us that we truly tune the Fermi level through the gap. So if we are somewhere around 0 top gate voltage, then we are with the Fermi level in the conduction band. If we are out here somewhere, we are in the valence band, and somewhere along the way, probably where the resistance is more or less the highest, we are with the Fermi level inside the gap. And so now I'm going to show you actually how the magnetic images look like. So if we take a magnetic image out here and out here, this is what it gets. So in color, I show the flux detected by the SQUID, and then as a function of x and y position. And then you see kind of outlined the whole bar here. And this looks rather homogeneous, but to convince you that something interesting is going on, I'll also show you the image which we actually get when we scan with a top gate voltage really at the top of the resistance peak. And so you already see that the pictures are dramatically different, just the magnetic image. And actually just by looking at the magnetic image, I can hopefully convince you that you really see in one image more something like a ribbon current, which I approximate here as a series of many small wires carrying a current. And the other image looks much more like two current-carrying wires, where one wire, this wire carries a bit more current than this wire, let's say. So because if you think, so these are roughly the field lines, the magnetic field lines you would get in the two cases. And if you now think about what the Z component of the field does as you scan across this, then this is a profile you would get in the case of the ribbon current, and this is the profile of the Z component of the magnetic field you would get in the case of the two current-carrying wires. And so then we can have a look at the data again. So now also showing a cross-section through the image taken off the resistance peak, and indeed we get a very smooth ribbon current looking like magnetic profile. And then if we take a line cut through the image which is taken on top of the resistance peak, we actually do see that it looks a whole lot like this picture where you have the two current carrying wires. Okay, so this is already a good, this already tells you quite firmly that there's really current flowing along the edge in this device. We can do still a little bit better because
how long does it take to take that?
the images?
Images.
it's not so terribly long. This maybe takes 20 minutes or so. It depends. So this was actually taken at, let's say, 150 nanoamps. And so there are reasons why, like 150 nanoamps is translates to a bias voltage in these devices, which is quite a bit higher than what transport people normally would apply. So we've also done checks down to like 10 and 5 nanoamps. And then I had to average a lot more, and then it takes more of the order of like 4 or 5 hours maybe. But yeah.
What's the spatial resolution?
It will come in a bit, but actually I haven't pointed that out when I'm talking about the SQUID. The SQUID pickup loop is like roughly lithographically 3 micrometer in size, and that also pretty much together with the scan height sets the spatial resolution to be like 7 micrometers. So that's I'll discuss it a little bit more, but like we can show that the current is really flowing along the edge. We don't get an accurate picture of the edge channel. For instance, these edge channels should have a characteristic width, and that should also change with gating. But that's something which we simply can't see due to our spatial resolution. Yes.
Roughly, what would that expected width be?
So I think really at the sort of the direct point, it's somewhere in the tens of nanometers. It's a bit. There's different, so I think they can, in principle or in theory, get very fat if you come to the bottom of the conduction band or the top of the valence band. But lately I've seen more and more calculations coming out, or like within, I guess it's not published, but like if you do a more, it depends a lot on the quantum wire thickness, because that determines the details of the band structure. And so it does depend quite a bit on the details of the band structure, how exactly the thickness of the quantum well actually evolves as a function of where your Fermi level is. Yeah. But somewhere in the tens of nanometers, I think, would be a good number. But, yeah. Yeah?
Just a simple question. If you have current going in the incoming direction, would you expect the magnetic field to be parallel to the front? Which direction is the field, magnetic field?
I mean, you get the. Oh, do you mean the? Did I do the right-hand rule wrong, or?
The left case.
Hmm?
The left case, when you have current going in the incoming direction.
Yeah, so the current goes into the board, right? And then I'm sort of like using like the right-hand rule to.
So the field is going parallel to the.
Yeah. I see. So you say that there's no Z component to this. Yeah. No. It's a very. I mean, it becomes 0 in the middle, right? Like if I would make this ribbon wider and wider, then the center part of this thing will become very flat. But like it's sort of like truly 0, only exactly in the center. But there's a small But it will become smoother and smoother. So we can do. I'm not doing so great on time. So to get from 2D current to flux, what you have to do is like you have a current density. You use Biot-Savart law to compute the Z component of the magnetic field at a specific height, which in our case is like 1 to 2 micrometer, and then you have to convolute that whole image with a point spread function of the SQUID, as written here, and we actually do know our point spread function to some degree by looking at superconducting vortices in a good superconductor. We can say more about that at a later point, but so that would be the forward problem. The good news is, since we know the point spread function, this whole procedure is invertible. In the case of two-dimensional current flow, you can actually invert Biot-Savart's law, and we use that doing fast Fourier transforms, because this convolution here, and in a sense this is also a convolution here, in Fourier space just become divisions. Yeah.
So your point spread function is determined by the size of that loop as well as how close you get it to the
Yeah.
sample, right?
Yeah. Yeah, it's both. It's
A smaller loop, of course, would give you more resolution, but
Yeah.
take longer averaging.
Yeah, actually we are. So we are like John Berkeley is working on the next generation of the SQUIDs in collaboration with IBM at Yorktown Heights. And so in that next generation there will be SQUIDs with down to 300 nanometer size pickup loops, and then hopefully we'll get a better spatial resolution. The point spread function makes us a little bit nervous. The point spread function of these smaller pickup loops for various reasons might be a bit more complicated. But we hope for better resolution soon. And then there's also a whole other community which are nanosquids. Like, I don't know, Eli Zeldorf at Weizmann Institute, they actually make these squids on like pulled quartz fibers. And they have like, I think sizes of like 100 to 200 nanometers pickup loop. But they have, of course, yeah, then your signature noise also goes down. Yeah, that's fair enough. Yeah.
So since you have large fields in the other directions that you're not measuring, how accurate is the orientation so that you project those non-z direction labels?
Oh, okay. I mean, it's like the alignment angle is roughly 4 degrees. So we convince ourselves that just like sine of 4 degrees is a relatively small number. But I think it kind
it's
of
a
works.
small number, but at least the way you drew it, looks like you've got a big field in that direction.
That's a fair point. I should think about that maybe more carefully. Yeah. It might, yeah. I guess especially for the ribbon current, that would make a big difference. Yeah, yeah. I'll think about it. Yeah. Okay. So now we've covered this. Now that the resolution is pretty much limited by the size of the pickup loop and the scan height. And yeah. So now we actually have a way to go from the magnetic image back to a current density, and that's what's shown here. So now here's again the magnetic image I showed previously, and now I also plot the current density along, or the x component of the current density and the y component of the current density. And you see that in this case, you really get a fairly smooth current density which spreads out through the whole bulk of your device. And the same in JY, you see sort of the current coming into the device and then sort of spreading out here and going back into the right contact up there. And you get a very different picture if you actually look at the magnetic image and the corresponding current densities, which are taken directly up at the resistance peak. So you really see the current going along the upper edge here, and you also see a smaller fraction of the current actually going along the lower edge. And what is kind of cute is that you really see it tracing out the whole lower edge of the Hall bar, including going into the two contacts down here. And you even see that in the Y component, that you sort of like go down into the contact and come out of it again up there. And so yes, so this really tells us the current is really flowing along the edges in these devices. But the width of the current peaks I show you here are really limited by the resolution. So they have no information about the actual width of the edge channels in this structure. And then we can also play games like continuously tuning actually through the gap, as you see here. And things to see is like, well, I'll point that out in a second. So what is interesting here is actually that you really see also now regions up here on the peak, and once we come down here again, where you see current along the edge coexistent with some current in the bulk. And that's kind of a nice feature that we can sort of like distinguish these two, because when you measure transport, you won't be able to tell what fraction of the current flows through the bulk and which fraction flows through the edge. And so this movie is nice, but I'll show you now. I should hurry up a little bit. I'll show you a few line cuts. So here you see line cuts taken through the middle of the Hall bar as a function of top gate voltage. So these are the line cuts through the magnetic images here, and these are line cuts through the current density, the x component of the current density as a function of top gate. And so again, so the yellow one has mainly current along the edges. The dark blue ones have mainly current through the bulk. And then you have some intermediate ones, like the purple one here, which really has current along the edges, but also some current through the bulk. And so they really can coexist, which is interesting to know. And we can even go and analyze this further by actually filling each of these line cuts with a sum of 3 contributions. One where the current is sort of 100% flowing along the top edge, one where the current is 100% flowing through the bulk, and one where the current is 100% flowing through the bottom edge. And then these 3 weighing factors sort of give you the fraction of the current which flows through the top, the bottom, and the bulk. And that is how that looks as a function of top gate voltage. So you see here, for instance, the red diamonds are the fraction of the current that flows through the bulk, and you see as a function of top gate voltage that this really initially is 100%, but then once you reach the gap, drops to pretty much 0 and then comes up again. Whereas if you look at the top edge, for instance, you see that it carries almost no current at these top gate voltages, but then carries a lot of the current up here when you're in the gap. And one other thing, or one step which we can do still with this data, is to actually ask if we now assume a very simplified model, and that is assume that the edges, or the top edge at least, and the bulk conduct in parallel, from these fractions we can actually compute what the sort of effective resistance of the edge and the bulk would be. And that the effective resistance is then just given by actually the measured resistance divided by the fraction of current in the, for instance, bulk, and that would give you the effective resistance of the bulk. And you see that as a function of top gate voltage, the bulk becomes pretty much insulating, but then the top edge, in comparison with the bulk, actually stays at a relatively constant resistance. And that is kind of interesting because that tells you that the bulk and the edges coexist. And even stronger, at the onset of the bulk conduction, there doesn't seem to be so much happening to your edge channel. And so that's now something which sort of can maybe help to understand a little bit like issues like how actually the bulk and these edge channels couple together. And there are different scenarios why or why not they might not couple so well to each other. Yes?
Why is there so much asymmetry between the top and the bottom channel?
Yeah, so so first of all, the bottom carries a lot less current, and actually that's I might not come to that anymore, but like we've measured one other sample, and there the ratio between top and bottom was actually different, so it's somehow sample specific. That it has this double hump here. That is because the bottom and the top edge, the bottom edge and the bulk are slightly coupled in the sense that the current somehow has to make it from these top contacts, it has to make it to the bottom edge to actually end up as a current there. And once your bulk gets conductive, actually a fraction of the current can sort of cross over through the bulk directly to the bottom edge and then sort of be carried on by the bottom edge. And so that's why sort of the bottom, or the fraction of the current flowing along the bottom has these little maxima where the bulk is actually already conducting. Yeah. Yeah. All right. We've done, actually, this is on a different device, but a very similar measurement. We also have looked at how temperature affects how the current distributes in the whole bar. Here I actually only show magnetic field profiles, but we can do a very similar analysis as on the slide before. Here I show you what happens to the resistance of the whole device as a function of temperature, and then extracted from this data how much current flows in the bulk and along the edges. And then again we can look at these effective resistances and see that actually the change or the major change in resistance of the device really comes from the bulk conducting a whole lot better, probably just because through thermal activation, and that not so much is actually happening to the edge resistance itself. And so that again is also interesting because there's a lot of like work going on about the temperature dependence of the resistance of these edge channels. This is coming a little bit to the question which was just asked. How much current flows along the top path and the bottom path. In one device we found really at the resistance peak a ratio of 1 to 8, and the second device we found a ratio which was somewhere between 1 to 2. You can ask yourself, like, what would you expect? For perfectly ballistic edge channels, you would actually expect a ratio 1 to 5. And if your edge channels are completely diffusive, non-ballistic at all, you would expect a ratio of 1 to 1.6, which is simply given by the total length of edge along the top path and the total length of edge along the bottom path. And none of these two really matches what we see. And so ideally we would get a lot more statistics, but at least I can say that this is kind of consistent with a picture which quite a few people have now for the system, that what likely is happening is that you have pieces of, let's say, ballistic edge channel which are interrupted by scattering sites which are not well identified yet, but like these scattering sites are more present on a several micrometer length scale. And so if they are there on a several micrometer length scale, there's still, in devices which are, let's say, 50 micrometer in size, there's still a lot of like randomness and statistics expected from sample to sample. So this seems at least to be consistent with this, but it might also be more subtle than what I just said.
So you've not tried it on smaller devices? You've not done this on smaller devices to look to see what the size dependence is?
We could do it on smaller devices, but I'll tell you very briefly about like a measurement we're planning, which is not imaging the current flow, but which might give much better information about the size dependence actually. Okay, so we can also, like, I did something really bad to the device, and in fact I shocked the top gate, and it's kind of fun. So in transport you would see this, that your resistance peak got a lot more ugly, but actually if you can image, you can actually see that really something bad happened to your device, and that like there's a really weird charged landscape probably in your gate dielectric suddenly present, which makes it different regions of your whole ball gate differently. We've done so far, that's a very important point. So far I can show you that the current flows along the edges. There's no proof in all the data I've shown you that there's anything topological at all about it, right? I can see the spin polarization, I can see the size of the edge channel, and so there might be also trivial scenarios why the current flows along the edge. For instance, banding comes to mind, which is present in some materials. And so the only way we can address that experimentally is that we've also done measurements on a non-inverted Hall bar, which was 5 nanometer in width. And so there's a cap. And that Hall bar has seen like the same processing and fabrication as the Hall bars, which are made out of the thicker Telluride layer. This is the 2-terminal resistance. The Hall bar goes insulating, and so that's a problem, because if you want to image current flow through an insulator, that's not really possible, right? So the best we can do is we can creep up on the resistance peak and sort of convince ourselves that even so while going up on the resistance peak, we see no indications at all of edge channel transport. And I think that's still a fair assessment, because in the case of the inverted devices, just by already going up on the resistance peak, we actually see fairly clear indications of the edge channel transport. Even though the transport isn't dominated by the edge channels yet, you do see their presence. And so in this case, we didn't see anything of edge channel transport. But Okay, so that's as good a control experiment as we can do, I think, with our current technique. I'd like to very briefly mention, I don't have much time, so you can look it up on arXiv. There have been 2 other scanning probe experiments on this system recently coming out of Stanford, one directly out of the group of David Gordon using scan gate microscopy, and then there's been another work from the group of ZX Shen using scanning microwave impedance microscopy, and you find them both on arXiv. And very recently we've also been, and that's work by Eric Spenton, which is a third-year graduate student in Cam's group. We've just used the same way of imaging, looking at indium arsenide, gallium antinomide quantum wells, which are predicted and seem to also realize the quantum spin Hall state. They have the problem that the bulk is not fully insulating when you tune it into the gap. So Eric's measurements kind of show that there's indeed also in these samples some current flowing along the edges when you tune the resistance to its peak value. But it's still the bulk here still carries also a lot of the current. But there's improvements on the way from the material side actually. So actually they report in recent talks that they have now made structures where the bulk is a whole lot more insulating than previously. And so very briefly to come back to the length dependence actually, and the measurement we are planning now is actually to not image the current flow anymore, but to start looking at persistent currents around holes in the same material. So a persistent current is given by the derivative of the total free energy with respect to flux, and it's something which in my group, for instance, Henrik Bloom has measured on small rings made out of gold. So the idea being if you thread a ring with a flux that you get these persistent currents around it. In the case of a 2D topological insulator, you just need to make a hole and just the edge channels themselves sort of make that you are naturally in a ring geometry. And so then we can go in with, that's where this field coil comes actually in, we can go in and thread the hole with flux using the field coil, and the pickup loop will then sense the magnetic moment which is generated by this flowing persistent current. And this is kind of an interesting measurement because it's we'll be able to hopefully be able to do measure temperature dependence of this persistent current. We'll also be able in a single sample to sort of measure many different holes of different size or circumference, so that will address the length dependence actually. We'll also be able to take a lot of statistics by measuring many nominally identical holes, and I think that's a much more suitable measurement to actually gather statistics about this. Yeah, so I hope I have convinced you that the current flows along the edge of the quantum spin Hall regime, that the bulk and the edges can coexist. I hope that you kind of think that the scanning SQUID is a convenient tool to image transport. It's nice because it's compatible with top-gated devices, and we can also apply it to other materials. There's still many open questions. I think the only one I might have addressed partially is actually what is the coupling between bulk and edge, or at least we provide some data based on which we can try to understand this better. And then in the near future, we hope to do these persistent current measurements on holes into the topological insulators. Thanks.